Welcome to the Science Voyage, your journey into the wonders of the universe. Today, we will embark on an incredible adventure through time and space to explore one of the most profound questions in science. How did the universe begin? Our story starts with the Big Bang. But what exactly is the Big Bang? Contrary to what the name suggests, the Big Bang was not an explosion in space. It was an expansion of space itself. Imagine blowing up a balloon. As you blow, the surface of the balloon expands. In a similar way, the Big Bang was the rapid expansion of space-time. Let's rewind the cosmic clock to about 13.8 billion years ago. At this point, the universe was incredibly hot and dense, a state we call a singularity. This singularity contained all the energy and matter of the universe in a space smaller than a single atom. Exciting, right? In the very first fraction of a second, the universe underwent a period of exponential expansion known as cosmic inflation. During this brief time, the universe expanded faster than the speed of light. This might sound strange, but it's perfectly consistent with the Einstein's theory of general relativity, because it's space itself that's expanding, not object moving through the space. As the universe expanded, it began to cool. About 1 second after the Big Bang, the temperature dropped enough for protons and neutrons to form from the quark-gluon plasma. These protons and neutrons are the building blocks of the atomic nuclei. Over the next few minutes, the universe cooled further, and the protons and neutrons began to combine to form a nuclei of the lightest element, hydrogen, helium, and tiny bit of the lithium. This process is known as Big Bang nucleosynthesis. Fast forward to about 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with this nuclei, forming neutral atoms. This era is known as recombination. With the formation of neutral atoms, photons could finally travel freely through space, leading to the release of what we call the cosmic microwave background radiation, or CMB for short. The CMB is like a snapshot of the oldest light in our universe, a faint glow left over from the Big Bang, permeating all of space. This radiation gives us a picture of the universe when it was just 380,000 years old and provides crucial evidence for the Big Bang theory. After the release of the CMB, the universe entered a period known as Dark Ages. During this time, there were no stars or galaxies, just clouds of neutral hydrogen. It was not until about 400 million years after the Big Bang that the first stars began to form, marking the end of the Dark Ages and the beginning of the epoch of reionization. These first stars and galaxies reionized the universe, splitting the hydrogen atoms back into protons and electrons and allowing light to travel freely once more. As time went on, these early stars grouped together to form the first galaxies. Gravity pulled matter together into larger and larger structures, creating the vast cosmic web we observe today. Over billions of years, galaxies merged and evolved, giving rise to the rich and diverse universe we see around us. But the story does not end there. Observations of distant galaxies shows that the universe is still expanding, and not only that, the rate of this expansion is accelerating. This discovery made in the late 20th century suggests the existence of a mysterious force we call dark energy. Dark energy makes up about 70% of the total energy content of the universe, yet we still know very little about its true nature. Alongside dark energy, there is another mysterious component called dark matter. Unlike ordinary matter, dark matter does not emit or absorb light, making it invisible to our telescopes. However, we can infer its presence through its gravitational effects on galaxies and clusters of galaxies. Dark matter makes up about 27% of the universe, leaving just 5% of the ordinary matter that makes up stars, planets, and everything we can see. So, what does the future hold for our universe? There are a few scenarios scientists consider. If dark energy continues to drive the accelerated expansion, the universe could keep expanding forever, leading to a big freeze, where galaxies drift apart and stars burn out, leaving a cold, dark, and empty cosmos. Alternatively, if dark energy changes over time, it could lead to a big crunch, where the universe eventually collapses back into a hot, dense state, possibly triggering another Big Bang. Another possibility is the Big Rip, where the expansion becomes so extreme that it tears galaxies, stars, and even atoms apart. Thank you for joining me on the Science Voyage. Stay tuned for more adventures into the wonders of science. Don't forget to like, share, and subscribe for more exciting explorations. If you have any questions, feel free to ask in the comment section below. Until next time, keep wondering and keep exploring. Bye.